In this little video, I would like to address the core process of the speech recognition, which is the classification problem. As you know, in the first stage of the recognizer, we have extracted a temporal sequence of features, calculated, for example, as Möller frequency capsule coefficients. And now for each of these feature vectors, we need to find the corresponding phonemes. And the phonemes can then be combined in order to form words or sentences. This is usually done with statistical processes, and in particular, two types of processes have been found useful in the past for addressing this problem. The first is called a hidden Markov model, or HMM, and the second is the one of neural networks, or NNs. Let's first address the hidden Markov model. In the picture, you can see a particular type of hidden Markov model, which is called a discrete hidden Markov model. It consists of a sequence of states, which are the little blue balls here. And you see with the arrows and the numbers on top, you see transitions between the states. So there's a probability of 40% or 0.4 to have a transition from state 1 to state 2. You see that there are only transition probabilities from left to right, which is a very useful characteristic of such a hidden Markov model, which facilitates the computation in the training process. You also see that there are certain transitions from one state to itself, so-called self-transitions, and there are also probabilities for jumping over a state. All these come with certain probabilities, which you see by the numbers. This particular type of hidden Markov model also has another type of probability, which is called an emission probability, and this emission probability defines how likely it is that a certain state in the model emits a certain symbol, generates a certain symbol. In this case, you see phonetic symbols on top, each coming with certain probabilities. Now, such a model can be used to calculate the overall probability that this sequence of states generates a certain sequence of symbols. Let's calculate, for example, the probability that this pre-trained model generates the sequence heben, which corresponds to the German lift. So we can calculate this probability by multiplying the probability that this state number 1 emits the symbol h, which is 1.0 or 100%, multiplied with 0.4, which is the probability of transiting to state number 2, multiplied with 0.8, which is the probability to emit the symbol e, multiplied with 0.2, which is the probability of transiting to state number 3, multiplied with 1.0, which is the probability to emit the symbol b, multiplied with 0.6 to transit to state number 4, multiplied with 1.0, which is the probability to emit the symbol e, multiplied with 0.5 to transit to state number 5, multiplied with 0.6 to produce the symbol n. And all this product of different probabilities generates the overall probability that this pre-trained hidden Markov model has produced the sequence of symbols heben, corresponding to lift. Now, in the heben, in the pronunciation of heben, you can have certain parts lengthened, produced a little bit longer than others, and you can easily do that by generating the self-transitions from one state to itself. You could also say heben, which would then omit the symbol here in the middle by jumping over that corresponding state. So this is a quite handy and flexible tool in order to generate the probabilities of sequences from a sequence of states. The low side of this model is that it does not allow to directly connect to the sequence of feature vectors which we had at the input of the speech recognizer. In order to use that input information, we need to make use of a different type of hidden Markov model, which is called a continuous phoneme hidden Markov model, because it models the context of a phoneme, usually by taking 3 states. One is the state for running into that phoneme from a previous sound, from a previous phoneme, and one of running to the next phoneme, because there is a certain influence of the neighboring phonemes on how I pronounce the middle phoneme. Now, in contrast to the discrete hidden Markov model, these states, of course, have transition probabilities, but they emit not symbols, but they emit continuous feature vectors. So there is a certain emission probability that this state generates a certain feature vector which corresponds of a number of certain values, and for each of the values you have usually a Gaussian distribution function. So this is a multivariate Gaussian emission probability for this state emitting a certain feature vector. And you can easily imagine that these blue vectors which you see here on the slide, that they correspond to the colorful spectrogram pictures which you have seen on the previous slide, so that there is a probabilistic link between the sequence of states to this colorful spectrogram picture to the feature sequence. The probabilities, the multivariate probabilities, are shown here on the top. Now again, you can calculate the overall probability that a certain sequence of states which correspond by the training process to a certain phoneme has produced a certain sequence of feature vectors. And that's actually what we want. We want to have the probability that a certain observed sequence of feature vectors corresponds to a certain sequence of phonemes. So this actually is the type of hidden Markov model which can be used in order to classify these phonemes feature vectors belong to. This approach of hidden Markov model has been proven very successful in the past, but it was superseded by another type of statistical model which has become more popular recently, although it has been used before as well. And this is the so-called neural network. Neural networks are particular types of machine learning algorithms, and machine learning is a field of study in artificial intelligence that focuses on developing algorithms and models that enable computers to learn and make predictions or decisions based on data without being explicitly programmed, so without having any explicit knowledge we put into the system. This learning needs to be done with the help of data, and depending on what type of data you have, there are different approaches to machine learning. The more popular one is the supervised learning, which learns from labeled data. And I've put here into brackets that it's a high amount of labeled data. This is one of the major limitations of machine learning, that you need lots of labeled data in order to train it. There are other semi-supervised learning principles which learn from both labeled and unlabeled data to make it more robust to predict for new unseen data. And there are also so-called unsupervised learning principles which learn patterns and structures from unlabeled data. One particular interesting type of unsupervised learning is so-called self-supervised learning, which learns from unlabeled data by predicting hidden parts or corrupted parts in a sequence of input vectors. And this is a model which has been proven rather productive and helpful in the recent years. There are other approaches to machine learning, for example, reinforcement learning, that learns from interacting with an environment by maximizing a reward or minimizing a set of penalties. And the goal is then to learn a policy that maximizes the overall cumulative reward over time. In the following examples, which I will present for automatic speech recognition, we'll mainly make use of supervised and self-supervised learning principles. But now let's find out what a neural network actually is. And we'll start with a very simple principle which is called a perceptron. A perceptron is in principle a very simple linear classifier which allows you to classify a vector of input consisting of the features x0 to xn minus 1 into an output, and this output can only have two values, class A or class B, +1 or -1. This output is calculated by taking each component of the input vector, multiplying it with the corresponding weighting value, subtracting a bias, summing all this up, and putting it to a thresholding function, usually an S-shaped function, which allows you to classify the input into the two classes. Now for a two-dimensional input, x0 and x1, so in a plane, this would correspond to a straight line classifying the space into two classes A and B. The simple linear classification is not enough for many problems. As you see here in the lower example, you have distributions of A here and there, and B's here and there, and they cannot easily be divided into two classes. So the simple single layer perceptron would not be good enough for this type of problem. But we can model more complex nonlinear problems by combining several of such perceptrons. And they are combined usually in a layered way, so organizing the perceptrons in layers which take the same input values, so we have the same input feature vector here, and the outputs of the first layer are then fed to the subsequent layer, so they are used as input to the subsequent perceptrons. And this can go several times. Here we have displayed only 2 hidden layers, but in practice you can have more than 2 hidden layers. And then in the output you would generate the different classes, for example the different phonemes which you want to recognize, 26, 20-something in a certain language. Now this multi-layer perceptron can be trained efficiently and was successful for automatic speech recognition, although it was not good enough to compete with hidden Markov model, at least for most parts of the speech recognition process. In recent years, that has been changed by including more knowledge about the temporal structure of the speech signal into the perceptron network. As you see here in this simple so-called feed-forward network, you just have a feature vector at the input and you have a class at the output. But you have no information about the temporal development of the input vector over time. This can be resolved by making recurrence to previous state, that is by putting memory into such a hidden Markov model, and this is called a recurrent neural network. One particularly successful way of doing this is by using so-called long short-term memory, or LSTM. You see LSTM as a block here, as a cell, which has certain input and output values, and which includes a memory. And that's very important because an LSTM cell allows an update of the memory to keep important information in the network. This information is an aggregation over time. As you see here, in the input, you have the input features at certain subsequent moments of time, T0, T1, T2, T3, and the same also for the output. So you have the output labeled for each instance of time. A top-level diagram of the LSTM network for a sequence length of 4 time step is presented in the figure behind me. It shows the frame-wise features xi that are used as input to the LSTM blocks, which go from left to right. These are labeled here LSTM plus blocks. And you see that there is a certain pipeline of these blocks, one after the other. And at the same time, there is another pipeline of LSTM blocks, which go from right to left. These are labeled here LSTM minus. So you have basically a forward direction and a backward direction of the network, which makes it a bidirectional LSTM network. At each time step, the LSTM network receives as input the frame-wise features of the current time step and the LSTM output of the previous time step. And consequently, at the end of the sequence, the network saw all of the individual time steps. That is, it can take into account all the different instances of time, and by this, the temporal development of the speech signal. The outputs of the forward and backward LSTM network at each time step are then concatenated to yield the updated output feature vectors, which you see here for each time step on the lower end of the picture. And usually such a network is trained by supervised learning algorithms, which requires quite a lot of data. In very recent years, transformer networks have shown to outperform this type of LSTM network in many tasks, especially in natural language processing tasks, but also in speech recognition tasks. The transformer model consists of an encoder network that processes an input sequence and a decoder network that generates an output sequence. So it's a sequence-to-sequence architecture. The encoder mainly consists of a multi-head self-attention layer with a subsequent feed-forward layer, which you see here on the left-hand side. This transform block is repeated multiple times to create a deep neural network by stacking several of these transformer blocks on top of each other. The self-attention mechanism allows the input of a time step to attend to other time steps, rendering an interaction between the different time steps at different time intervals from the current point in time possible. The input to the transformer block, frames on the left side, is a sequence of frames. In this case of speech recognition, it's the frame-wise features. And this input sequence is processed by the multi-head self-attention sublayer with the following feed-forward sublayer. The other layers, which are depicted here in yellow, are used for normalization of the weights while training. To allow for the addition of inputs and outputs, all sublayers in the model must produce output of the same dimension, of the same length. As a consequence, at first, a fully connected network is applied to the input sequence X to yield a sequence X slash, which you see here, with vectors of equal length at each time step. The transformer block is then stacked multiple times to yield a deep neural network, and the output feature sequence is Y, where each time step vector is updated with relevant information from the other time steps. The multi-head self-attention mechanism is depicted here again on the right-hand side of the picture. For every time step of the input sequence, a query, a key, and a value are calculated through a matrix multiplication with a set of 3 learnable weight matrices, which are implemented as fully connected layers, which you see here below. This mechanism allows the model to jointly attend to information from different representation subspaces at different positions in the input sequence. So they can make use of information at different levels of temporal distance from the current moment in time. These transformer models using a self-attention mechanism have been proven very helpful in the processing of speech and language data. They're usually trained by unsupervised learning, so no human labeled data is necessary in order to train such a network, and that makes it particularly attractive also to train with large amounts of data, because you don't need labels for that. Now you have seen the process of classifying sequence of input vectors, of feature vectors, into a sequence of symbols, of phonemes. And these phonemes can, of course, be combined to words which are loud according to a certain language, that is the vocabulary. And then these words usually come in certain sequences. So the language defines which words may follow each other. Putting that information explicitly in the model also helps to boost the recognition performance. That is, we are after finding language models which contain information about possible or probable sequences of words. Usually, there is a grammar which defines what is allowed in a certain language and on what is not allowed. In principle, we can use such a grammar, that is, we can define a set of rules which define whether a certain sequence of words is allowed in a certain language. In computer science terms, this is called a context-free grammar, which can, for example, be expressed as you see here in the upper part. So you have a start symbol, and then you have non-terminal symbols like the sentence, which can be a positive or negative sentence. And the positive sentence can, for example, contain the words yes or yep or yes please. And the negative statement could, for example, contain no or nope or no thank you. That would be a very simple grammar, only for a very particular purpose, namely saying yes or no. And you can imagine that you can build more larger sets of rules which govern the production of such a language. The disadvantage of such an approach is that it is exclusive. That is, it does not allow any other sequences of words other than the ones which are defined by those rules. Especially in spontaneous speech recognition, the language we produce does not always obey these rules. This is why a statistical approach also to language modeling is more helpful. Statistical language model means that we produce probabilities that a word occurs in a certain context, that this word occurs after a certain other word, that is called a bigram, or that it occurs after 2 other words have been produced. This is called a trigram. So we can produce statistics about how frequent is a word in a certain corpus, how frequent are combinations of two words in a certain context, and how frequent are combinations of three words in a certain context. These are called the unigrams, the bigrams, and the trigrams. And usually we don't go for longer context than for trigrams. Now these statistical language models, they might better reflect what we actually encounter in real-life situations, and they can be calculated by counting the frequency of words in large corpora. Recently, also deep neural networks have been used to better model the order of words in certain languages. These deep neural networks are again based on transformer architectures and use unsupervised training on large corpora of text. And as you have seen, also the classification problem can be based on transformer-based neural networks. So we can think of perhaps doing the entire speech recognition process as a big neural network. And this can be done and has been proposed in recent years. A very popular approach for this is so-called wave-to-vec or wave-to-vec 2.0 here, which is illustrated in the slide which you see behind me. Unlike other speech recognition models that rely on the conversion of the audio to spectrograms and then Mel frequency capsule coefficients, and then having a separate phoneme classifier and then a separate decoder stage, the wave-to-vec approach uses the waveform of the audio directly, which you see on the lower end of this picture. During the training phase, it learns to automatically extract meaningful features from the audio waveforms, which can then be used as an input for another model, such as a classical neural network, or the decoder part of a pre-trained transformer network, which you see here. The waveform is usually first processed by a convolutional neural network. That's a particular type of neural network that is frequently used in image recognition and processing. And here it processes basically the waveform of the speech signal, so no longer images. The training of such a wave-to-vec model is usually done through self-supervised learning. That is, we train the model by removing certain parts of the audio waveform, just blocking it here. And then the model needs to learn what is this missing part. So it needs to learn the structure, the temporal structure of the features of the waveform, which belongs to these features directly. Through this method, the model learns to extract meaningful features from the entire waveform and to connect them to form a coherent context without being explicitly told to use a certain type of feature extraction, a spectrogram or a Mel frequency capsule coefficient or raster coefficients or something like that. So the model learns that automatically. This wave-to-vec approach is also referred to as an end-to-end recognition approach, as the model is trained and then used for recognition without requiring intermediate explicit steps, generating the text directly from the speech signal.